Hi, everybody. I'm Mike Dahm, and welcome. As of exactly right now, you are the Toronto C++ user group. The land on which we're meeting has been a site of human activity for 15,000 years. We recognize the enduring presence of indigenous people connected to and on this land. We're grateful for the opportunity to gather here and work in this community, and we commit ourselves to the work of reconciliation with the indigenous peoples. First of all, I'd like to thank our hosting sponsor, Autodesk. They provided this room for us and the delicious food that we all just ate. Afterwards, we'll follow with dessert and more time to chat. Yeah, why not? In particular, I want to thank Casey Concepcion from Autodesk. She did all of the food. Casey's up there, so you can see. Took care of all of the logistics. I'd like to thank my wife, Lanny, hiding in the corner, who has helped me lent me her secret powers for the night. My co-organizer, Jason Walter. My spiritual guide, Kate Gregory. And our first speaker, Jon Kalb, who has also provided a tremendous amount of organizational know-how and guidance. I will also want to put in a plug for Include C++. If you're not familiar with it, it's a global, inclusive, and diverse community for developers who are interested in C++. If you haven't been, there's a Discord, which is it's a chat server run by Include C++, where you can go and find the most knowledgeable, nicest people to talk to at all times. It's global, so really at all times. They know more than me. They might know more than you. And they are happy to help and answer questions on any subject that you like. So I recommend you go and sign on right after this meeting. Okay, we have some upcoming C++ events that I want to mention. C++ Now is going to be May 5th to May 10th, coming right up. CPPCon has just opened its registration, and that'll be held on September 15th to 20th. And the call for papers is out. The deadline for that is May 20th. In addition, there's the first ever Core C++ conference in Tel Aviv. That'll be May 14th to 17th. And 2 conferences in Europe, CPPP on June 15th in Paris, and the Italian C++ conference in Milan. That'll be on June 15th. So I'd like to introduce our speaker, Jon Kalb. You might have noticed there were 3 bullet points on the upcoming C++ events related to C++ Now and CPPCon. Well, Jon is the conference chair of both of those conferences. So if you have any questions, feel free to ask him afterwards. When Jon started programming C++ professionally, the annotated C++ reference manual was only 1 year old. There were no books by Scott Myers, Herb Sutter, or Andrei Alexandrescu. The GCC C++ compiler was a year old. There were no C++ compilers from Microsoft or LLVM. There was no cppreference.com or godbolt.org. There was no Boost. There was no STL. There was no ISO standard or standards committee for C++. But tonight, Jon is here to talk about C++ today. Thank you, Jon.
All righty. So I have this, am I good? All right. I have this little quiz that I give while we're warming up. But we had a great warm-up, but the quiz was up and people were asking me questions about it. So I'm going to go through the quiz kind of fast, and then we'll get to the real talk. But first I want to say, I want to congratulate Mike. You guys have, I was telling Kate, there is not a user group in the country, and believe me, I know about the user groups. There's not a one that wouldn't be delighted to have this kind of turnout. Most of the user groups, this is what they try to build to. And you guys, Mike, you've done this right out of the gate. This is absolutely phenomenal. You guys are going to have a great group. I can tell. There's great energy here. I'm so excited to be part of this. This is just terrific. All right, so the question is std string a user-defined type? And somebody said, well, that's obviously a trick question. I said, okay, what's the answer? It's, well, I'm not sure. Well, if you're not sure, then that's not a trick question. All right, so what's the answer? How many of you put up your hands, put up your EastCon's badges. How many of you think it is a user-defined type? Okay, how many of you think it is not a user-defined type? Okay, there's a lot of people didn't put a hand up because they think I'm recording it or something. I'm going to turn you into the standards committee. Here's the deal. I asked a number of people who are on the standards committee, and almost all of them said yes. No, I'm sorry. They said no. They said that's not a user-defined type. It's defined by the standard. Now, you have to understand, most of the people I asked, they're on the library committee. Just because that's who I knew, I asked them. If you ask Bjarne Strustrup, it's very clear. Because the standard doesn't define what a user-defined type is. It uses the term many times, but it never defines it. And Bjarne, in his book, he defines what it is. And according to Bjarne, this would be a user-defined type. Even though it's defined by the standard, it is not, in fact, built into the language, and so it's defined by users. So from Bjarne's point of view, this is a user-defined type. But as I said, I talked to a number of people on the standards committee. Now, the standard's a little wishy-washy about this, because in some areas, it's pretty clear that, again, the standard is saying that if it's not built into the language, then it's a user-defined type. But in other areas, it's also pretty clear. I shouldn't say it's clear. It's not clear. It seems to be by implication that the standard is saying that it's only a user-defined type if a non-standard user defines this. And here's what the difference is. The people who are in the standards committee who are working on the language, that is the core, they think that's user-defined. It's done by the library. Whereas people in the library think, wait a minute, if the standards committee defines it, it's not user-defined. So the standard doesn't actually define this, and I would like to see the standard define it, and then they have to come up with a term for defined by non-standard users, because they don't have that distinction. Okay, does the following line include a header? It's pound include mytype.hpp. Now, those of you who are really paranoid are thinking there's some Unicode character that John put there, so it doesn't actually, no. It's nothing tricky here. All I'm asking is mytype.hpp, is that a header? And of course, you guys have all been programming long enough to know, of course, that's a header. That's a header, right? But my question is, how well do you know the standard? What is the standard's definition of a header? The standard actually is clear about what a header is. A header is something that is included with angle brackets. If it's in quotes, that's not a header. That is a user file. Okay? All right. So what you and I think of as a header is just, it's included to compile things. No. The standard says it's only a header is only a file that is in angle brackets. And furthermore, the standard in one place actually tells you what the headers are. Those are the ones that are defined by the standard. If you go to Boost and you pull it in angle brackets, well, that's not a header. That's a user-defined that you're pulling in with angle brackets, right? But another place in the standard actually refers to some POSIX headers as headers. So it's a little unclear in that area. Okay, so the last thing I want to ask about is, what iterator category requirement, and just to be clear, I'll tell you what I mean by an iterator category requirement. The category requirements are input, output, forward, bidirectional, random access. Those are the category requirements. What are the iterator category requirements for the generic algorithms lower bound, upper bound, and equal range? Now, we all know what lower bound, upper bound, and equal range do, right? They use what algorithm? Those are all binary search algorithms, right? So we know we're trying to do a binary search. Which of these iterator categories would you need in order to do that? Random access. John's tricking me somehow because it's so obvious, right? It's random access. You and I think it's random access, but if you read the standard only requires bidirectional. Now, wait a minute. If you tried to implement this with bidirectional, what would the performance be? Now, what would we expect the performance be of a binary search? What should I expect of binary search? Should be log n, right? Am I going to get that if I have bidirectional? No. But what does the standard say? Well, the standard's very clear, and it says that it will be log n in comparisons. It ignores the traversal time of the iterator. But now wait a minute. If I have a function that part of it is log n and part of it is linear, as I scale up, which is going to dominate? The worst, right? So anyway, that was the questions. What do you know about the standard? This is my question. What would be the order of complexity? And you answered correctly that the order is not what we expect if we do, in fact, have forward iterators. OK. That was just the warm-up. Now we're going to talk about what I'm here to talk about, which is C++ today. The beast is back. That's me. And this is the book that I wrote with my friend Gasper Asman. And actually, the book itself is kind of the subject of the talk. And by that, what I mean is that O'Reilly paid us to write this book. They didn't pay us very much. But they paid us to write this book. And they literally give it away. Right? I mean, you can go online, and with your email address, you can download an ebook of this free. And when they printed out, they printed out a bunch of hard copies, too. Oh, excuse me. I know. I'm not supposed to do this. Oops. So here's the book. I don't have very many hard copies left, but this is the book. So you can see it's really booklet. All right. So they gave it away. They took it to conferences, and they gave it away. They literally gave it away. So with a price of 0, but they paid us to write it. Now, somebody might look at that and say, oh, that Tim O'Reilly guy, he's a complete idiot. He pays people to write books that he gives away free. Anybody actually think Tim O'Reilly's a complete idiot? I'm not seeing any hands. Obviously not. What's he doing? Well, this is actually a business for, I was going to put the link up there, too. Yeah, you can do that. Go to that link. This is actually part of their business. They will pick up-and-coming technologies and print what they call a report on it to give it away free, because what they're trying to figure out is who should we market this to when we write books that are longer and that we're going to sell for money. Now, you notice, what did I say there? I said, what kind of technologies? Up-and-coming technologies. You know, people don't normally think of C++ as the up-and-coming technology. But in fact, as I said, O'Reilly's not idiots. They know, they spot a trend when they spot one. They know a trend when they see one. And that's what this talk is really about. Because what we really want to talk about is the fact that C++ is, and has been now for a number of years, on the rise. It's coming back. The beast is back. So how many of you recognize what that is? What is it? The Babbage Engine. So you probably know then who's peeking out behind there, right? That's Charles Babbage. This is the difference engine. Now, actually, this isn't the one he built. It's a replica built to this standard. And the reason I'm talking about it is because we're talking about computers, and I want to go back to kind of the very early computers, because the very early computers, the algorithms for handling the data were actually part of the hardware of the computer, right? Because basically the data was a bunch of those knobs inside there, those gears, but how it was processed was something the computer itself knew. But who knows who this guy is? Von Neumann, yes. He did an interesting thing. He made an observation. He said, you know, computers, they hold data, and they process this data with instructions. But you know, the instructions themselves are really just data. So a computer should be able to hold the instructions that it uses to process its data. And when a computer is designed that way, we call that a von Neumann machine, which is essentially what all of modern computing are. They're all von Neumann machines. The software is, in fact, in the memory of the machine. It's part of the data that the computer itself uses. And when we talk about data, what is our data made up of? Get all the way down to the bottom, what do we have? What is our data made up of? Ones and zeros, right? It doesn't matter what it is. Is it a string? It's made up of a bunch of ones. Is it a color? Ones and zeros. Is it an image? It's made up of a bunch of ones and zeros. All ones and zeros. And so that's actually what the data itself, that is the instructions, it's all a bunch of ones and zeros. So what we have here is, anybody recognize what this is? Assembly for what platform? $6502. Congratulations, Mark. You are way older than, well, I better be careful what I say. All right, so Mark recognizes this is 6502 assembler. But the point is that what we are doing is the instructions, just like everything else in the computer, are just a bunch of numbers. But it's hard for we as humans to think about numbers. We don't want to say, oh, register 6, 42, register 5. We don't want to do that. We want to think of mnemonics, and so that's what this is. It's a language that's made up that makes it easier for us to remember what these commands are. Now, the interesting thing about this is that we call it assembly language when, in fact, that's the wrong idea about assembly language, because there is no an assembly language, right? Every platform has its own unique assembly language because every platform has its own unique set of instructions. But if you really want to do systems programming, of course, you're going to want to use assembly language. So if you're a systems programmer, then you need to be able to access anything about the machine. If the machine does something, you need to be able to control it, and that means you're going to want to have that kind of power, and you also want to have performance, because if you're the systems programmer, your code is at the bottom of the stack, and everyone runs your code. So your code has to be really fast. Those application programmers, they can slack off, but the systems programmer's got to be fast, right? Okay. But what if you are, in fact, a scientist? What are your concerns there? Do you really, really need to do every esoteric feature of the machine? No. What do you want? You want code that is going to help you solve your problems, whatever formulas you need cranked out, and you don't care if there's some interesting feature of the machine. You don't need that. What you need is code that can run on a machine if you have this machine, and take that code somewhere else and run it there. Do you need the absolute power? Probably not. You want to be able to crank some serious numbers because you've got hard problems, but you don't need to squeeze the last little bit of the machine, and you don't need to have all that. So what do we have? We have a language, right, from John Bacchus. Gave us Fortran specifically for scientists so that they could write code that they could take from machine to machine, make it portable. This code is not great code for doing system software. If you really need to control things in the machine, this is not really the best way to do it. But if what you want to do is write code that's understandable for someone translating formulas, which is where the name comes from, and being able to move from machine to machine, this is what you do. But what if you're a business person? You have the same situation. Now, you're not trying to do scientific formulas, but you want to do processing. And again, you want to be able to use the hardware that's available, and you may not need to find all the features of that hardware. So we have a language for you. Who gave us this language? Grace Hopper. Grace Hopper gave us COBOL, right? This is for common business language, COBOL, common business language, okay? All right. Can anybody recognize what this is? This is the user console, not the entire machine, for a Univac. So the Univac was, came out in the early 50s, and it was the hardware equivalent of COBOL. In other words, it was for businesses. In fact, it was marketed as for government and business. And what kinds of things does it have in it? Well, it has things like text processing, because businesses need to do text processing. And it has BCD. All right, what's BCD? Binary coded decimal, right? So what is binary coded decimal? It's a way of encoding so that you can count all the way to 10 in registers that could go to 16, right? We're throwing away some performance. Why do we do that? Well, it's because if you're writing an assembly language and you want to think in terms of decimal digits, this makes so much easier, right? So this machine came with BCD instructions. Compare now to this machine. This machine was from the early 60s. It's called a Link. It was a scientific machine. It was sold into laboratories. Didn't do BCD. Didn't have great text processing. What did it have? What did it have that the Univac didn't have? That's right, floating point. Floating point, right? Because you're a scientist, and decimal numbers are not as interesting to you as floating point numbers. All right, so that takes us up now into the 60s. And something happened in the 1960s. The leading computer hardware maker of the day was IBM. And they released a machine, really a platform, a family of machines, that was so much of a step forward that they absolutely cemented their lead. They went from being a leader of a group to being the obvious leader of the group, right? They made this. What is this? The IBM 360. Do you see that red dot? Can everybody see the red dot? The panic button, right? Because this came out when there were all these movies like the Fortran Project and these, computers taking over the world. And so there had to be a way to stop it. And if you hit that big red button, the machine will stop. So we're safe, right? Yeah, we don't have, paranoia about artificial intelligence today. That was back then. All right. But the interesting thing is the name, the 360. I used to work for Boeing. So I know the first Boeing jumbo jet was the 707. And I know what that number stands for. I know what it means. We all have the whole Boeing series. There's the 707, the 727, 47, the J7. I worked at Boeing. I know what those numbers mean. Does anybody here know what those numbers mean? They mean absolutely nothing. Marketing thought 707 sounded maybe a little James Bondish, high-tech, jet set. So that's what we call it. So when I saw the IBM 360, my first assumption, of course, was that 360 didn't mean anything. Somebody just thought it sounded cool. But I was wrong. The 360 actually means something. Does anybody know what the 360 means? Somebody's doing this. Maybe he's saying, wrap it up, John. We're running a little long here. No. The idea is that it was 360 degrees. The idea is that this platform could handle all of your computing needs, country and Western, right? It could do, now one new computer fills all your data processing needs. It can do business and science, both of them, everything. Now, what does that mean? Well, what that means is that it had binary, BCD, and hexadecimal floating point calculations. And what they essentially did was they said, if there's an instruction set that you want, we're going to have it there. And that made the instruction set so complicated that they basically used microcode. They had to program the instruction set itself. And this was the first computer to do that. And they did something else. Now, they weren't the first to do this. But they were such an influential thing that they made this the standard. And that was 8-bit byte addressing. Now, you have to understand that today, we all know what a byte is. What's a byte? It's 8 bits. Of course it is. But this is not the obvious decision that it might seem to be. In the early days of computer hardware, there were a lot of different experimentations. There were computers that had 10-bit words, right? So a byte was 10 bits. There were also 36-bit words. So a single word could have 5 characters with a leftover bit. So it's 35, because a character is what? ASCII is only 7 bits. So a character fits in 7 bits. And then you have this leftover bit, which tells you if you're at the end of the string or not, and you have to carry on. I don't know what, But why would you build a computer where the character, the addressable space is only once every 36 bits? Why would you do that? You're saving on address lines, right? You don't need very many address lines if your address resolution is only down to the 36 bits. But if you want to do efficient text processing, and there were, in fact, for machines that had larger words, that very often there would be instructions that say, take this number of bits out of this thing and process that. And you had to do that. Whereas what IBM decided with the 360 was, look, we're going to do an address down to 8 bits. Every single character is going to be addressable, have its own address space. And that just works so nice from a programming point of view that it caught on. And in fact, you could argue that IBM, with the IBM 360, established what we would call the C machine architecture, a byte addressable machine with registers. It was the C machine architecture, but it was 10 years before C. Okay, speaking of C, we're now at the 1970s. All right, it's getting cool. What is this? What? Bell Labs. That's right, this is Bell Labs. All right, so Bell Labs has a few things that are really, really important for us to invent Unix. And one of those things is they had some really smart people, like Brian Kernighan, just hanging around. They also had a need for Unix. It turns out that at Bell Labs, this was a research area, and so they were generating lots of patents. You know, it was a big company putting a lot of money in it. It was more for the prestige. They weren't generating a lot of money, but they were generating a lot of patents. And so Bell Labs had its own patent office, not like the US Patent Office, because nobody filed patents with them. The patent office at Bell Labs filed patents with, right? And when you file a patent, it's supposed to look nice, so they had to pay people to do typesetting. And Brian Kernighan went to the patent office and he said, you know, if you would get me this unused PDP-8 sitting here and let me use it, I'll build you a typesetting system. So for those of you who are using Unix or have used Unix, which I assume is most of us, if you ever used nroff or troff, those utilities are the reason Unix exists. It was to run those applications. We build this entire operating system in order to run the utilities to do that. Not this particular machine, by the way. This was actually in Scandinavia somewhere, but it is a PDP-8. All right, so this is what happened. He got his deal. He got a chance to create Unix. What was Unix written in? Who knows what Unix is written in? Everybody knows Unix is written in C. No, it was not. I said earlier, if you're doing systems programming, what do you code in? It was done in assembly language. It was done on a PDP-8. It was done in assembly language for the PDP-8. But the issue is, as it becomes more successful, we begin to realize, you know, we would like to run this on something other than a PDP. And if we do that, we've got a choice. And the choice is we got to rewrite the whole thing in a different assembly language, or perhaps we could do something different. And so with Unix version 4, the undertaking was to rewrite all of the operating system in a new language that was designed to be a portable assembler. It was for systems programming what COBOL was for business programmers, and Fortran was for Fortran is for science programmers. It was for systems programmers. And this was a bit of a questionable decision because people said, wait a minute, you're systems programmers. You should be writing an assembler. You want to be as fast as possible, and you want to control the machine completely. You don't need a high-level language. But of course, it turned out to be very, very popular because systems programmers are just like everybody else. We don't want to have to know the very arcane, esoteric things about the hardware. If I can write something that's portable, that's what I want to do. Now, of course, this is a different kind of language. It has to lend itself to low-level things. It has to be extensible. It has to get out of the way when I really do need to link with assembly language or do low-level kinds of things. But that's what this was done. And so that we have Dennis Ritchie making C this incredibly successful and powerful language. It does, in fact, become the programming language for systems programming. One of the limitations, though, seems to be, and this is opinion, so I'm here to share you my opinion, but I'll label it as opinion. As you start to write more and more complicated things in C, and there's a debatable number, but I've heard people say at 50,000 lines of code. At 50,000 lines of code, a C application is starting to get complicated enough that you're wishing that you had better ways to abstract away that complication. And that's one of the weaknesses of C is that it's great at the low-level stuff, but it doesn't necessarily abstract well for really higher, more complicated kinds of systems. All right, so now we reach the 1980s. But now that I've got to the 1980s, I'm now going to step back, and I'm going to talk about these two guys. Can you read the name? Who are these guys? Dahl and Nygaard. Who are they? Oh, come on, you should know them. They won a Turing Award. They won a Turing Award for ideas fundamental to the emergence of object-oriented programming through their design of the programming languages Simula 1 and Simula 67. Well, it just so happens that this guy over here, Christian Nygaard, he was a faculty member at this little town in Denmark. And one of his students, one of his graduate students at this little town in Denmark, was a guy named Bjarne Stroustrup. And so he was, of course, taught how to do object-oriented programming, and he was taught how to do it in Simula. Then Bjarne got his, it was a graduate degree, but it wasn't his PhD. Bjarne got to go to Churchill College in Oxford, no, in Cambridge, sorry, to get his PhD. And he wrote his dissertation, and to do that, he wrote a program to simulate a network, to simulate network behavior in a program. Now, it's a simulation. What language did he write it in? Simula, yes. That's what, he was a good student of Kirsten. He understood object-oriented programming, and he understood Simula, and he wrote his thesis project was to get data on this. And so he ran it on the computer there. He ran it until the administrators pulled the plug because his program bogged down the entire system. It wasn't capable of doing it. So what happened next was so important that I'm going to break an important rule of presentation, and I'm going to read you some words on the screen. I know this is bad to do, but it's so important I want to stress it to you. So this is what Bjarne said. He said, so I rewrote my simulator from Simula into BCPL. So BCPL was a predecessor of C. He said, and all of the high-level structure disappeared. All of the nice organization that had helped me debug and helped me design disappeared. But the resulting BCPL, once I had debugged it and lost half my hair in the process, ran really fast. It could use all the resources of the machine. It could communicate with anything on the machine, and I got my data, and I got my PhD. I came away with the opinion that I would never again want to attack a problem with tools that were fundamentally unsuitable. And in particular, I don't want to make the choice between elegant, which Simula was for this problem, and efficient, which BCPL was. I want both. And that has been sort of one of my guiding lights. If you give people the choice of writing good code or fast code, there's something wrong. Good code should be fast. That is an important design idea about C++, is that we want to be able to have high-level abstractions. We want to be able to think at the high level about what it is we are processing. What is our domain? If we have a domain that involves X, we want to have objects that represent X. And that's what we want. But we aren't willing to pay a performance penalty to that. It still has to be fast. It has to be efficient. We've got to figure out how to get the abstractions without having the overhead. So Bjarne got his PhD, and he got a job working at Bell Labs. So this is the research place. So he goes to Bell Labs. Bell Labs, you know, he learns about C because that's taken over the C. He, of course, knew BCPL, so it was a natural for him. And he starts working on extending the C language to have some of these high-level abstractions. He initially calls it C with classes, but eventually the pun is so wonderful that he calls it C++. Now, one of the questions that's been asked of Bjarne, and I think I'm gonna channel him for a second and talk about what this question is and why he answered it, because I think it's very insightful for us in the C++ world. The question was, in retrospect, do you not feel like it was a mistake to base C++ on C, given that it had certain, syntactical baggage? And Bjarne's answer was, if I hadn't based it on C, I would just have based it on something else. Because Bjarne knew there were, even way back then, there were hundreds of failed programming languages that didn't catch, that didn't take off. Bjarne didn't want to write another one of those. He wanted to start with something that was a proven success, which C was. C was very popular. If you wanted to do systems programming, C had all the features you needed. And so using that as a starting point, it was a trade-off. If he had started from scratch, he could have avoided some of the syntactic baggage that C gives us. But by accepting that baggage, he got in exchange a language that was perfectly good to do systems programming in. And that was worth it to him. It was a practical trade-off. I'm accepting some imperfections to get something that works. It was very, very practical. And C++ is, if nothing else, a very practical language. All right. So the language becomes quite successful. AT&T thinks of it as an important language, but they think of it as an important language for internal use. They don't spend any resources to promote it externally. It's not like some of the languages that we know where some big company said, we want to get a bunch of people to adopt this language so that they will work on our platform or for whatever reason. AT&T just basically said, yeah, we'll publish it and we'll give it away, but we're not going to promote it. And it turns out that during the 1980s, the number of C++ users doubled every 7 months. It really took off. It hit a sweet spot. And so I'm going to stop talking a little bit about history and actually ask the question, why is it that it was so accepted? What is it about C++ that made it a hit with software engineers? So, and I'm not going to go through all these things, but we're going to talk about this high-level abstraction idea, that you get the high-level abstractions, what Simula gave you, but you get it with low cost instead of some of the trade-offs that Simula had made. You get low-level access when you need it. I think it's obvious why you get that, given that it's essentially a superset of what was the most successful portable assembler at the time, and still is. A wide range of applicability, highly portable, and better resource management. So let's take a look. Again, I'm not going to go through all these. All these things are essentially abstractions of one sort or another. They allow us to think about code at a slightly higher level than actually thinking about the bits and bytes and registers that are involved in that. Just these kinds of tools here. And I am going to zero out the first one, or zero in on the first one, the user-defined types. And the reason is, in C++, the way we solve a problem is we create a new type. That's just what we do. You have a problem, we'll have to have a type to solve that problem. And what that means is that if you're using C++, the ability to define a type has to be low overhead, right? If we create a type and suddenly that means, oh, it has to be registered with the system and it has to, have a certain amount of bytes allocated to it and all these no, if there's overhead, we couldn't do that. Can't be like that. So the user-defined types in C++ have the power and expressiveness of built-in types. There are really very few, there are a few, but there are very few things that you can do with built-in types that you can't also do with your user-defined types. And as time goes on, the standards committee is making more and more of these things that you can do. So an example is, it used to be that a non-type template parameter had to be something like an int, something like that. Now we're expanding that and saying, oh, you want a non-type parameter that's a color? You define what it is? We can do that. Right? These are the kinds of things that over time, they're more and more reduced. But again, the point is that almost anything that you can do with a built-in type, you can do with a user-defined type. One of the examples we want to talk about are some of the fundamental arithmetic types. So because of our ability to do operator overloading, we can take a user-defined type and make it work just like a built-in arithmetic type. So for example, in the standard library, we have complex for complex numbers. What's a complex number? It's something that's partly real and partly imaginary. Okay? Now notice, nobody is ever saying, well, you know what? We should make those built into the language. Let's not just put them in the library, let's put them in the language because we'd get better performance. Nobody says that. Why? Because you wouldn't get better performance. The implementation of complex numbers in the library is pretty much optimal. You're not going to get anything better just by building it into the compiler. Right? And why is that? It's because the language allows us to have that kind of power with our user-defined types. Object pointers. We have an object pointer in the standard, unique pointer. If you look at the code generated when you use unique pointer and you compare it to the code that you would generate by using naked pointers, you will see it is exactly the same code. The overhead of using a smart pointer, if the smart pointer happens to be a unique pointer, is nothing. There is no abstraction penalty for using a pointer that guarantees you're not going to leak. And I want to also talk about function objects. The function pointer. Again, it turns out that if you are calling generic algorithms and you have the option of passing in a pointer to a function or passing in a function object, if the function object has inline operator, it is actually more efficient to use the function object than to use a real function pointer that is native to the language. That is how powerful you can be in using user-defined types in C++. And that's very important to us because, as I said, how do we solve problems in C++? We define a new type. That's what we do. So it's really important that that's powerful. One of the things I want to talk about is, and one of the things that made it popular is, no programming paradigm is forced on you. You want to be an object-oriented programmer? This was one of the first successful object-oriented programming languages. You don't like object-oriented programming? You want to sit next to Alex Stepanov? You guys are going to have a lot in common. And you're both going to be able to use C++. You just won't be able to use the virtual keyword. But that's fine, because there's room for all of these kinds of things, all of these different approaches, and you can mix them. You have to understand the strengths and weaknesses of the different paradigms and the sharp edges when you try to mix them, but you can mix them. There's nothing in the language that says you can't take your object-oriented programming with a bunch of pointers to objects and put those pointers into a vector or some other generic container. All of these things can be mixed. Okay, libraries. I actually think of C++ as a language for building libraries, right? Because I think of types as essentially a library. What is a type? Oh, it's a library. It's something you're going to use. So how do we solve problems? We make a type. That's a library. It's something that some user is going to use. That's the library. We can have, because in C++, libraries are designed to be powerful, efficient, safe. Because of our ability to overload, operator overloading, we can have natural syntax. And we can even use type-specific optimizations even when writing generic code. All of these things are available to us. Our generic features we can have that are as efficient as custom code because of that ability to take advantage of type-specific optimizations. Bjarne has talked about having little or no abstraction penalty. Bjarne talks about his goal as the zero overhead principle. And I want to clarify exactly what that means, because some people assume that means that you're not going to have any overhead. That's not what it actually means. The zero overhead principle means two things. One is, if you don't use the feature, you pay nothing. If you don't use the feature, you pay nothing. That makes sense. That's zero overhead. But the other one is, if you do use it, you pay no more than you would if coded by hand. So if you use a virtual function, is there overhead associated with virtual? Yes. Suppose you said, oh, I don't want to use virtual functions. There's overhead associated with virtual functions. I'm going to write my own system for doing type dispatch at runtime, and mine's going to be more efficient than a virtual function. No, it's not, right? Because the overhead that you get by using the feature is no more than you would get if you were hand coding the feature. That's what the zero overhead principle is. And with very small exceptions, everything in the C++ library, everything in the C++ language follows that kind of principle. That you don't pay for it if you don't use it, and if you do use it, the cost is comparable to what you would incur if you wrote it by hand. That's a very high bar, but it is exactly the bar that the C++ Standards Committee embraces. And in fact, one of the things that the Standards Committee insists on is that there isn't room for a more efficient language underneath C++. We just can't have that. That's not our model. If you were to go to the Standards Committee right now and say, you know, there isn't a good way in C++, and this is true, there isn't a good way in C++ to really exploit the GPU. But I've got an extension to the language that will allow you to exploit the GPU in a general way. You'd be really popular. Everybody'd love that. Unless somebody looked at your proposal and said, yeah, but you know, you're not really as efficient as you could be. someone else could come up with a language that would do this better. That's going to kill your proposal, because that's the standard that the standards committee holds itself to. That is the standard. That's a high standard, and it means that our libraries and some of our features aren't as wonderful as some other languages, but we do not compromise on performance. All right, systems programming. Well, this one's pretty easy because all these things come for free. The price we paid for working with the syntax that C adopted, which wasn't beautiful in all ways, that price we paid, we get paid back in the fact that you want to do systems programming, you need to deal with bits and bytes, you need to control how things are laid out in memory. That problem has all been solved with C, and we just borrowed it. Management, low-level access when you need it. If you need management of user-defined types, this example is most object-oriented languages have some way of saying, I need to create an object, so I need memory, and then I need to initialize that memory in some way. In C++, we call it a constructor, but the point is, all object-oriented languages have some way of creating an object and getting it ready for use. In most object-oriented languages, if you have an object that is an object-oriented object, you have to allocate that on the heap. That's just part of the language. That's just understood that if you're creating an object, you're going to put it on the heap. That's not good enough for C++. In C++, you could take that object, and instead of just putting it on the heap, which of course you can do, you could put it static. You could give it the lifetime of the application. Or you could put it on the stack. Now, putting something on the stack gives you way fewer options than putting it on the heap. Lifetime-wise, you don't have as many options. However, the cost of putting something on the stack is significantly less than allocating it and later freeing it on the heap. So if your solution does lend itself to being able to put your objects on the stack, you have that option. Heap, static, stack, that's still not enough for C++ programmers. I want to be able to put it wherever I want, whenever I want, and I want to control it. And in fact, in C++, you can do that. You can say, I want to call the new operator, and I want it to create the object right here. And I will control the lifetime of that object. And that is, in fact, what the vector class does. Arbitrarily creates and destroys objects at arbitrary times, at arbitrary points in memory. That's the kind of thing that is expected of C++. Again, low-level access, we're talking about cache optimization. So one of the things that you hear about if you go to C++ conferences is caching. When the first year of CPPCon, I'd been working with C++ now. I had a pretty good idea about conferences, but I was very worried. Was the conference going to do well? Were the audience going to be happy? So I was hanging out in the hallway waiting for people to come out of sessions. And on the very first day of the conference, it was in the afternoon. There had been 4 sessions. And this fellow was coming out, and I overheard him say to the person who was walking out with him, he said, I get it already. It's all about caching. I talked to him, and it turned out in every session he had been in, there was a discussion of the difference between a cache hit and a cache miss. By the way, this is getting a little sidetracked, but I got to tell you this story because I love it so much. My goal for CPPCon is to make a platform for all C++ users to talk to each other. And I feel like C++ is sometimes kind of a collection of islands, right? Mark was talking about doing video stuff. And then there are games people. And then there are people who, somebody here told me they do cute stuff. There are people who are doing defense stuff. And a lot of times they're not talking to each other. And that's what CPPCon was supposed to be. I want everybody together talking. And so my idea was, let's find someone who is a game developer, because I know that's a group that is big, it's visible, and it doesn't really talk with mainstream C++. We're not communicating the way we should be. So I reached out to, I'm not a games person. I know of exactly one famous game developer, and he wasn't available. But somebody came to me and said, how about Mike Acton? And I said, I've never heard of him, but that doesn't mean anything, because other than this one guy, I haven't heard of anybody. I said, would other game developers have heard of him? Oh, yeah. He's kind of the bad boy of the game community. I said, okay, that sounds great. Once he gets me hooked, though, the guy says to me, now I have to tell you, some of what he says might be controversial. I said, hey, that sounds great. We're trying to get this conference, build a name for ourselves. It turns out Mike Acton, who we have as one of our plenary speakers, hates C++. It's a really good way to start off a C++ conference, right? But he did something that was the most effective, again, like everybody else at the conference, he was talking about caching, right? But he did the most effective way of presenting it. Notice, this was the first year. We only had 600 people then. We have twice that many now. But we had 600 people in the room while he's giving his keynote speech. He says, okay, now I've scaled this up. I want everybody to see what happens when I try to load from memory and I have a cache hit. And this little progress bar goes, boom, great. He says, now I want to show you, again, this is scaled up, how long does it take when I have a cache miss? And there are 600 people in the audience trying to get this progress bar to crawl just a little bit faster. But he made the point better than anybody, right? Caching, so important. But, most languages don't talk much about caching. Why is that? It's because you can't control it anyway. One of the things that we talk about with caching is false sharing and figuring out how to avoid false sharing. But the reason we talk about that is because in C++, you can avoid it. If you want something laid out in memory in a certain way, you can control that. That's just not possible in most other languages. Okay? All right. Yes, in fact, if you want, you can use C++ containers that are designed to be cache-friendly. You want memory in contiguous strips. A lot of object-oriented programming languages, no. The object is on the heap, and it's put where it's put, and there's nothing contiguous about it. Whereas in C++, the library has a number of contiguous containers, and if you want to write your own, you can write your own. Bjarne's idea is don't solve the specific problem, solve the general one. What we as software engineers always ask are, as soon as we ask, does it work? The second question is what? Does it scale? It's great that it works, but if it doesn't scale, it's just interesting. It's not usable, right? It has to scale. One of the things about C++ is that not only does it have to scale up, meaning, we might have to run a search engine, and the search engine is going to be written in C++, right? But it may also have to scale down. We may have to write an embedded device. And we want to be able to do that with high level of abstraction, but we have to have amazing performance, and we also have to have no overhead if we don't need it. Again, scaling up and scaling down. And also, because of the ability to compile our programs in separate compilation units, one of the things about the system, about C++ is that, and I've worked on teams, I wouldn't say I've worked on the largest team in the world, but I've worked on large teams that were doing operating systems in C++. And you can have a team of 100 people. I suppose at Google, they probably have thousands of people working on the search engine. It's possible because the compiler doesn't have to see the entire code at one time. We compile it in chunks. And so not only does the application itself scale up and scale down, but the teams can scale up and scale down. Very important. All right, so the machine, C++ is highly portable because it's based on the C machine model. And we talked about that earlier. That goes all the way back to the hardware developed by IBM and the IBM 360. They weren't trying to target C, of course. C didn't exist then. But they had a particular machine model in mind, and that is the machine model that C and C++ are built for. I saw Alex Stepanoff was on a panel once, was with people from other languages. And of course, Alex is not one to shy away from ruffling some feathers. And he said on this panel, well, really, the only languages that you should actually spend any time trying to learn about are C and C++, because these are the only languages that are written for the machine model. Other languages try to create an idea of a machine, a virtual machine, that is not what the real machine is. And then they run their language on that. That works well if what you're trying to do is design a language that's easy to write or something like that. But if you really, really want performance, you have to get the real machine model, has to be your model of your machine. So that's what we have. And because of that, it makes it relatively easy to get C or C++ working on a new platform. And so most platforms out there do support one or sometimes multiple C++ tool chains. Okay. high portability. One of the things I want to talk about here is industry support. And that is, suppose I came to you and I said, hey, I have a great new language. This is so cool. The syntax, it's like butter. It melts in your mouth. It's got all the neat, cool stuff. You're going to love writing in this language. And you say, great, I got a project coming up. Let's hire a bunch of people for this project. And you say, what did you want to do? Well, you're not going to be able to hire anybody because, it's a great language, but nobody knows it yet. Well, that's okay. We'll just hire a bunch of smart people, and then we'll hire instructors to come in. You're going to tell me I can't get instructors. Okay, well, we'll just have to buy the books. There's no books on it? Well, we'll just watch the video. There's no videos, right? So it turns out that industry support is really, really important. No matter how good or bad your language is, industry support makes a big difference. Are there tools? Are there platforms? Can you hire teachers? Can you watch videos? Are there conferences? This industry support is really, really critical. And so this is how I look at C++. If you look at C++, one of its most important strengths is it can be used for system software. But it's not the only one. C can also be used for system software. D could be used for system software. Go, others. But one of the other important things about C++ is that it also has high-level abstraction. Whoops, we don't have C anymore. But we still have D, and we have Go, and Rust. These are languages that can be used for system software and also have higher-level abstractions. But what makes C++ unique is that it also has a level of industry support that those don't have. Now, some of those have great support because there's a big fan base or maybe there's a company behind them. But none of those languages has anything close to the support of C++. If you want a language that can be used for system software, that also supports high-level abstractions, and has huge industry buy-in, you're talking about one language, and that's C++. All right. I want to make one point about garbage collection. And garbage collection is trying to solve a really, really important and hard problem. So I'm not sure with this light if you guys can see this, but I actually have some gray hair. So some of you are laughing. I assume you can see the hair then. Every one of these gray hairs is a memory leak, right? So I've been through the desert. I appreciate the problem we're trying to solve. And I don't think that garbage collection is an awful solution. But it is a solution. It's an engineering solution. All engineering solutions have trade-offs. And so although garbage collection has a lot of things that are attractive, it also has some trade-offs that are made with garbage collection. One of the problems is that memory may not be released at all. Now, if all you're talking about is memory, maybe that's not a big deal. But if you're creating an object and you're saying, when this goes away, I want you to free the file descriptor that you're holding, or I want you to free up the socket, or I want you some other thing that we want to track. So the idea of having a collecting system that may, in fact, never collect, that's not sufficient for C++. In C++, when I'm finished with a resource, it needs to be released immediately. We may also have the problem that the garbage collection isn't totally under control of the programmer. So there may be times when, of course, the real truth is that there's never a good time, right? But you would like to be able to control it. You would like to say, at this point in my program, please do not start garbage collecting because this is a critical point. I don't want my application to freeze because I'm garbage collecting behind, right? Because it's outside the control of the programmer. And in fact, and I'm certainly not an expert on Android, but what I've been told is that your Android applications need to have a lot of unused memory, just because the garbage collector kind of requires a lot more memory than what you're actually in use. You have to have this unused memory. So this is a price you pay that a C++ would just not be acceptable in the C++ world. So we have to have a better way, and the system we use in C++ depends on a feature of the language called deterministic destruction. And we won't go into, I'm not going to show you any code tonight, but the idea is that we know at a particular point when we're going to have resources be released. And this is very, very powerful, and it does require a little bit of discipline on the part of the programmer, but if this discipline is properly followed, it has lots of performance wins over garbage collection. And we talked about earlier about the unique pointer, which allows us to do this with no overhead at all. And I want to talk a little bit about finally. So some languages have a way where we use some resources, and then we have a finally keyword which allows us to clean those up. The problem with that is that that violates DRY. What is DRY? Can you say it again?
Don't repeat yourself.
One more time?
Don't repeat yourself.
Can you?
I'm repeating myself.
All right. So what do we mean by don't repeat yourself? If I need to have cleanup for my resource, the C++ way would say I'm going to put that cleanup in the type. So every time I use the type, the cleanup happens automatically. If I have to have a finally keyword provided by the user, which is going to do cleanup, that is going to get overlooked at some point. I don't want to have to repeat that same code in lots of places. I'm going to make that part of the object, part of the type, with my deterministic destruction to clean setup. Okay? All right. Have you ever noticed that Michael Case's name is not presented enough in talks? All right. So now we're ready to get to the 1990s. Remember, I told you that during the 80s, the number of users of C++ was doubling every 7 months. 7 months. Now we're in the 90s. Do you know what the big thing was in the 90s? And I'm not talking about the hairstyles or grunge. What I'm talking about is in the programming world. What was the big thing in the 90s? No, you guys are ahead of yourself. You don't know. It's not Java yet. What it is, though, is object-oriented programming. This is going to solve all our problems. Because the problem is we keep having to rewrite the same code over and over again. Now we're going to put it in an object, and then we'll never have to write it again. Solution to all our problems. Some of you may be detecting a little bit of sarcasm. I'm OK with that, all right? But object-oriented programming was the big thing in the 90s, the big thing. And C++ was associated, C++ was the object-oriented programming language at the time. Now, despite the fact that I've been somewhat sarcastic about object-oriented programming as maybe being strongly hyped, the truth was that I think object-oriented programming has some places where it's really strong, and one of them is in building GUIs. And what was the 90s? The 90s was the decade of Mac versus Windows versus Top View, whatever it was. So the ability to make an object-oriented framework was a big deal, and what were they making them in? C++. C++ was all the rage. And in fact, in the 1990s, there were a number of companies that had made significant investment in C++ that went to Bjarne and said, Bjarne, we have this issue where our company has invested a lot of money in the language, and the fact that it is controlled by a guy in New Jersey, that kind of is a little bit of a problem. We want to start an international standard on C++. And Bjarne was, he didn't want to give up, but on the other hand, he realized it was a thing to do. So Bjarne is active even today, continues to be active with C++. This is something that you see in a lot of languages, that the originator kind of moves on. When you're not inventing the new language, when you want to maintain it, it's not as much fun. But C++ is something Bjarne has continued to work on. So this standards committee was formed in the 1990s and managed at the end of the 1998 to launch the first international standard for C++. But I want to talk about this guy. Because during the 90s, when everybody was talking about object-oriented programming, here was Alex Stepanov, who was not a big fan of object-oriented programming. He invented his own. He called it generic programming. That was his term, generic programming. And he was working on this library to allow him to write algorithms once and be able to use them across multiple different kinds of types, across multiple different kinds of containers, and really, really exploring how algorithms could be applied generically. And one of the fellows that was on the standards committee is a guy named Andrew Koenig. And Andrew and Alex had worked at Bell Labs. They knew each other. So Andrew sent a message to Alex and said, hey, are you going to propose your library to the standards committee to be part of the standard library? And Alex said, oh, no. He said that the standards committee is almost ready to release a standard. Well, He was about 4 years too early to say that. But he thought that at the time. A lot of people did think that at the time. He also said, you know what? This is also a much larger and more ambitious library than what the Standards Committee has looked at before. It's not like a string class. It's not like the stream classes. This is a more involved kind of thing. And he said, but the really killer is they're not going to understand it. And he knew that because, remember, this was the time of object-oriented programming. And I know because I was programming then. And I know what a container library in an object-oriented world looks like. What does it mean to put something in a container in an object-oriented world? How do you copy an object-oriented object? How do you do that? You copy the pointer. That's how you deal with objects. You don't really know what type it is. You don't know how big it is. All you know is it's the other end of this pointer. So to put something in an object-oriented container means I'm copying the pointer into the container. The container now owns it because the container is responsible for calling delete on it. That's what an object-oriented container is. So when I first got a look at the standard template library and I did my first container, I copied something into a vector. I said, no, I didn't. It's right here. It's not in the vector. It's right here. It didn't move. It's still here, right? Because it's so not the way we think of containers in the object-oriented world. Now, those of you who are younger, and I'm glad to see there's some young people here, you've seen the STL from the very beginning. You've not known anything else. So this all makes sense to you. But I guarantee you in the 1990s, the STL was really weird, right? And Alex was a researcher. He wasn't hiding this. He was presenting it to people, and they would get the kind of response, if it was a C++ programmer, would get the kind of response of like, yeah, this looks really interesting, but I don't know how it applies to anything I'm doing. And so he was reluctant to submit the submission to the Standards Committee. But what Andrew said is, Andrew's a pretty clever guy. Andrew said, you're right, Alex. The Standards Committee is not going to accept your proposal if you don't submit it. So Alex and his team went without sleep for a while as they made up a formal proposal of his library to the Standards Committee. And he was actually right. The first response of the Standards Committee was, whoa, 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 this is huge. And I should say, unlike me, they got the benefit of actually having Alex go to the Standards Committee and give a lecture explaining the ideas behind it. And I will credit the committee. They were a lot smarter than I was, and they were a lot faster at coming up to speed because the committee at first was reluctant to embrace this. But the more they talked about it, the more they recognized that they could not imagine releasing a standard that didn't have the STL in it. And so it did, in fact, become part of the standard template library. Okay? Or I should say it became the basis of the standard template library. All right. So I want to talk about this fellow. This is Beeman Dawes. Beeman was in charge of the Standards Committee in 1998, the library subcommittee, the working group, the library working group of the Standards Committee in 1998 when the standard was published. And one of the things that he understood was that the mission of the Standards Committee is to standardize existing practice. It is not really the mission of the Standards Committee, despite how they actually act sometimes, to sit down and invent a bunch of new stuff. That is not what they're supposed to be doing. What they're supposed to do is they're supposed to look and say, hey, here's a cool idea that's broadly used. Let's make that part of the standard. That's the way it's supposed to work. But the problem is, back in the 1990s, there were no open source libraries. All of the libraries that were in widespread use, all of them were proprietary. There were not any libraries that were what we think of now as just open source libraries where you go to a website and download it. There was no GitHub. It just wasn't. And that was a problem, and Beeman said, we got to solve this problem. If the future, we've made a release, we're happy about this release, but in the future we're going to want to have more libraries, and there is no widespread user base that's not proprietary, that we could standardize. So he worked with some other people on the Standards Committee, including Dave Abrahams, to create something called Boost. And what Boost is an open source library collection where the open source libraries are all peer-reviewed. So you can't just say, oh, I was working on this project, we never actually shipped it, but here's some cool libraries, and dump it. No, it doesn't work that way. You have to submit it, and you will be, your library will be reviewed, and there will be pushback, and it will be accepted only if you address the issues that have been raised. So we have a repository of high quality libraries available absolutely free on a language that is the language of object-oriented development during the decade that is the object-oriented programming decade that followed, growing at doubling rate of every 7 months. And now we are an international standard, and we have this open source library repository free, and the future is clearly going to be eaten by C++, right? Well, until we get to the 2000s, and something else happens, something called Java. So what is Java? Well, Java, it supports object-oriented programming. It's the language of the web, whatever that means. Oh, that means it's the language of the future. Okay, right? It's almost as fast. That's good. It's almost as fast. And it's easier to learn and teach. So you can almost imagine in your mind a phone call that's going on between some CS professor at some college calling up the department chair. And he says, hey, Dean, you know, I've been thinking about our object-oriented programming class where we're teaching object. Oh, yeah, that's really hot now. Everybody wants to learn object. Yeah, thinking about that. But you know what? If we switched from C++ to Java, we could skip all of Chapter 7. No pointers at all. I mean, you can see where that's coming from, right? All right, so let's talk about almost as fast. Well, it turns out that in the 2000s, our hardware, our processors were so fast that it seemed like we had essentially solved the performance problem permanently. Our processors were so fast that the operating system had to use gratuitous animations just to kill some speed so that you might upgrade your computer, right? So if that's the case, then why do you want to use a language that might be harder to use to get that little extra bit of speed? If you can get close with an easy-to-use language, shouldn't that be good enough? I mean, how fast does the cursor have to blink on your text editor? You just, at a certain speed, it doesn't matter. You can recompile your spreadsheets as fast as you need them. And so why pressure yourself for the last bit of speed with a language that has this baggage from the C syntax? It has all this complexity. It has templates, generic programming, which a lot of people still didn't understand, even though the STL was clearly a hit with some people. Operator overloading, so when you add 2 and 2, or I mean, it should say A and B, it goes off and formats your hard drive because you don't know what operator overloading is going to do because that's a user function. Who knows what that's going to do? And did I mention that pointers are hard? Right? So why do all this? You get a managed language that's fast enough. Well, what are we talking about here? Well, there were really 2 virtual machines out there. There's the Java family, and then there was the Microsoft CLI family. And colleges learned that it was easier to teach managed languages than it was to teach C++. Did I mention pointers are hard? Right? Okay. So that was one of the things that was happening in the 2000s. Something else happened. I said that the standard shipped when? First standard was 1998. And what happened to the Standards Committee in 1998? Well, you guys are software engineers. You ship software. What do you do when you ship software? After you get back from Hawaii, what do you do? Where do you go? Here. In California, we go to Hawaii. Where do you go here? You go to Hawaii. What a great place to go. All right. So, okay, you get back from Hawaii. You're ready to start work again. What do you do? What do you do? Well, first of all, you start working on all those features that you wish you'd had time for in version 1, but got bumped, right? But what else do you do? You work on the bugs. What else do you do? You're going to work on new features. Where do you get the new features? What? From the customer. You have shipped your product. The customer is now using it. And you tried to think of all the ways that would make the customer happy, but the customer always thinks of more ways, and so you get feedback from the customer. Here's a problem. You have to wind your head back. You're not used to it in today's now, when a new version of the standard comes out and there's a new version of Clang that supports it before the standard comes out, right? There's features in the standard that are not yet voted in the standard and already working in Clang. This was not the case in 1998. In 1998, this was not controversial. In 1998, everyone understood that there would not be a compiler or compiler and library combination that would support the standard for 4 or 5 years. I remember when the standard shipped and was really excited. Oh, I can't wait to use it. But everybody who announced that it shipped said, by the way, you won't actually get to use this standard for 4 or 5 years. Now, if your customers don't have your software for 4 or 5 years, what good is their feedback on the existing features, right? So that's the problem that the Standards Committee was faced with. That they had just released something that users weren't going to be able to use for 4 or 5 years. You know what happened to the Standards Committee? It shrank. People weren't interested anymore. They'd released a standard. They weren't going to add any more features. In fact, the committee itself kind of went into bug fix mode. They said, we don't want to start on new features until users are using the old ones, then we can get actual feedback from them. So the committee got small. And then came the next decade, the 2010s. I'm not sure when it exactly happened, 2010, 2011, but the beast came back. The beast came back in big ways. One of the things is Tim O'Reilly sent me money to write him a book about C++, because the beast is back. Let's take a look. First of all, it turns out that the performance problem that we thought was solved forever was just a blip. During the 2000s, we had really fast desktop machines, but it turns out that's not what a computer is anymore. This is a computer. And even if it's fast, I still want it to be efficient. Why? Because I don't want the battery to wear down. That's right? All right. So it turns out that mobile devices, you still want performance. You want performance with less power. So when we thought the performance problem was solved, it turns out that was just a blip. That was just a situation where the machines that we were running had plenty of power. But computers in general, and in fact, those computers outnumber the other computers quite a bit. But the other computing that's happening is in the cloud. I don't think there's a battery on that machine. But it's still very, very important from a point of view of performance. Why? Can't we just throw some more hardware at it? That doesn't scale very well. It turns out that we're still looking at performance. Performance per dollar of hardware, performance per watt of power, performance per watt of cooling. So there's a fellow named James Hamilton. While he was working for Amazon, he did a study. And he was looking at modern high-scale data centers. Now, I want to make it clear what I'm saying when I call it a modern high-scale data center. What he was looking at were data centers that were essentially running one piece of software. Maybe it's a search engine. Maybe it's the Amazon store. But it's a piece of software. It's not doing a lot of different jobs. It's lots and lots of hardware doing one job at scale. And what he found out was that in terms of decreasing cost, the highest cost then was servers. The money to buy the machines. Well, that's not really a surprise. They're expensive machines. The next one is power distribution and cooling. It actually costs more to get the power to the machine than to actually power the machine. The cooling is a more expensive problem than powering the machine. And then networking equipment, and then other infrastructure. So notice the top three are directly related to software performance. In fact, what he decided was if you could make your software 10% faster, you were going to drop your total costs by 9%. Almost 100% of your software improvements hit the bottom line. That has impact. That has huge impact. Now, wait a minute. Where are the programmers? Where's the IT professionals? Well, it turns out that at this scale, they are other infrastructure. They are a footnote, right? If you are trying to optimize for programmer time, you're optimizing for the wrong thing. Now, that doesn't mean there aren't languages where you want to do demos or you want to do some real quick thing. What we're talking about is a specific kind of application, and that is this high-scale application. At the high scale, you don't care about what it costs the programmer to get there. If they have to bleed a little bit, that's okay, because we're going to make it up by scaling large. Okay? All right. So the managed code optimized for the wrong thing. It optimized for programmer time instead of optimizing for performance on the machine. So we talked about what happened to the standards committee after C++ 98 shipped. What happened to the standards committee after C++ 11 shipped? What happened after 98? It got small. But something was very different in C++ 11. And the difference was that the tool vendors were tracking the changes very, very closely. And so there were actually working implementations of 2011 in 2012. It took about a year, and this is not a small change in the language, right? It feels like a new language. The page count almost doubled. There were tons and tons of new features. What kind of features? Well, some of them were simplifying by adding. One of the biggest problems we have in C++, you can ask anybody, and believe me, I have, what's the problem with C++? It's too complicated. Have any of you ever said, I'd really love this C++ language if it was just a little bit harder to understand? Who has said that? Not seeing a lot of hands here, right? It's too complicated. So how do you make it less complicated? Well, you just rip out some features, right? The problem is, what happens if you rip out features? You break your backward compatibility. Think about the value of the C++ software at your company. What would it take to recreate that software? Depends on the size of your company. It could be several $1 million, a few $1 billion, maybe $1 trillion. That's just your company. Think about the value of all of the C++ software in the world. The standards committee is not going to break all of that by destroying the backward compatibility story. That just isn't going to happen. We are going to continue to be backward compatible. But we still want to make it simpler, and it turns out that the standards committee can make some things simpler by adding. If you take away, you break. But if you add, and these are some of the things that are added. Auto, range-based for loops. If you don't know what the arrow is, don't worry about that. Enums, more consistent, uniform initialization. These are things that the standards committee said, we want to make it easier to learn C++. Now, that doesn't mean that we've ripped out all the features. What it means is it's now a little bit easier to think about modern code, making it easier. There's some other things that we expect in modern languages, like lambdas, better support for Unicode, maybe tuples, smart pointers. These are the things that modern languages have. C++ now caught up with these. A lot of these things have been available in Boost and other libraries, but now they're part of the standard. And then some things that you don't necessarily find in other languages, like better support for library authors. Remember, C++ is all about libraries. You may not, as an application developer, you might not care about better introspection of types at compile time. You may not care about variadic templates or perfect forwarding, but I guarantee you the libraries you use are going to make your life easier because those things are available. And then there's big new areas like multi-threading. Okay, maybe that's not so new. It's new to the standard, let's put it that way. And move semantics. Again, move semantics is the kind of thing that C++ programmers care about and other languages just wouldn't care about at all. It's way down in the weeds, but C++ programmers are concerned about where they can get their performance. What's this? It's a symbol for LLVM. It's their dragon. Actually, what is it called? A wyvern? A wyvern. Yeah, something like that. Okay, sorry. But what happened is, now this isn't new to 2010, because actually LLVM had been going on for a very long time. But from a C++ point of view, it was only at about 2010, maybe closer to 2011, 2012, that it became useful and interesting, because before then, the C++ compiler really wasn't up to it. It was doing C compiler great, but it wasn't until about this time period when LLVM started to have, with the Clang compiler, started to be able to do C++. In fact, as they were working on the C++ compiler, they knew that 11 was coming, and they were building those features in. So in 2012, Clang had an operating compiler that would compile C++ 2011. that was really when it started to get a lot of attention from people. One of the things was that it had huge improvements in error messages. You may forget about this now, but take a compiler from that time period and look at the error messages at the time and compare it to what the compilers, that same compiler today. Look at GCC's error message from then, compare it now. You will see how much improvement there is in error messages, and it came because Clang basically embarrassed everybody, right? And build performance. It takes years of building a compiler to get the code generation of really high quality. But build performance was an area that Clang was able to introduce from the very beginning. But just being a better compiler is not what I think is going to make what Clang memorable for. The real value of Clang and LLVM is the toolkit. Clang and LLVM were designed from the ground up not to be a compiler, but to be a toolkit for people wanting to do compiler-like work, to build analyzers, to be able to do feature testing for new features. And this is something that's very valuable. If you want to add a new feature to a language, what do? Well, you have to write your own compiler to put the feature on. If you're trying to use Microsoft's compiler, it turns out that's not open source. You could use GCC, but GCC was specifically designed to make that very difficult. They didn't want people to do those kinds of tools, whereas Clang and LLVM were built from the beginning to do that. And that's caused a lot more interest in C++ because people have been able to use it in more interesting ways. We've talked about open source. It turns out that if a compiler can actually see a source, which it can when templates are being compiled, they can do much better than just taking a .o file and merging a .o file. So C++, open source are great together. This is a little bit dated, but I also wanted to show you this interesting blip. This is on GitHub. It's not where you expect to see a lot of C++ because C++ tends to be a lot proprietary. There's a lot of very interesting free software available, but most C++ is proprietary. But notice we have this big blip come right there where C++ steps up in about the time frame we talked about, 2010 to 2011. So the committee, as we said in 98, shrank. But in C++, but in 2011, the committee did something that was a little bit unexpected. And that is, it got so big that it started to break up into all these different study groups. The committee decided that they were going to be more successful if they parallelize. It doesn't really make sense to have committees which just have a bunch more people. Let's have a bunch of subcommittees and break the work up. And these, I'm actually, I think we're up to 20 now. I think SG 20. So I'm missing some boxes here. And some of these boxes are actually no longer active meetings. But the point is that the size of the committee has grown dramatically, and a lot of it was because people began to see features being put into the standards committee and being used by users very quickly. In the old days, in the C++ 98 time frame, where it took 5 years for something in the standard to be used by users, contrast that today when literally there's a standards committee meeting in Kona and features get voted in, and you can look at Clang and GCC and Microsoft and see those features in the releases that are happening within weeks, because the teams are following this very carefully. And when you have that kind of response time, what it means is you don't even have to wait for the release. Users will see your features almost as soon as you can get it into the standard. That makes people very interested, and that makes more people attend the committee. And we will hope that increases the quality. We'll see. I do want to talk about this. This is basically a symbol for the C++ Standard Foundation. This is an organization that has tried to take on the role of publicizing C++. Remember I told you that most languages, or at least the successful languages, tend to have a big company that promotes that language so that they have more people developing for their software. There's nobody doing that for C++. C++ was developed by AT&T at Bell Labs, but they always saw it as an internal tool. They didn't care if anybody else used it. So they never tried to promote it. But the Standard Software Committee, Standard Software Foundation is trying to promote this, and so they actually have a website called ISO CPP. How many of you go to this website? If you are a C++ programmer, you should go to this website at least once a week, because it's going to be a clearinghouse for everything that's going on in the C++ community. It is nice that there's one place to go for that. So this is the website. They have a list of when standards meetings are coming, how to be involved in the standards process. They also have something else. They have this thing called a super FAQ. And what it is some of you may remember Usenet. There was a C++ FAQ on Usenet for many years. And Bjarne Strustrup on his home website also had a very large FAQ. They've actually merged those two together, and it's called the super FAQ, and it's actually a wiki. If you're interested in being able to ask and answer frequently asked questions, you can actually contribute to that. So here's the super FAQ. There's also a product that's come out in the last few years from Sea Lion. It is a cross-platform IDE for C and C++. I'm not mentioning it because of the tool. I'm mentioning it because of the research behind it. So the marketing that went on before, the market research that went on before Sea Lion came out into how big the community was. And so I've asked JetBrains to share this, and it turned out that Anastasia, who compiled it, she said, oh, happy to let you know, but she wanted to stress and make sure everybody understood where this information came from. The reason she wanted to stress that is because this may not really be great information. It may be the best information we have, but it was collected by essentially looking at jobs, job ads, maybe Stack Overflow. They did some user surveys. It's really hard to get this information. If somebody is writing C++ at some company and they want to be proprietary and they don't want to make a big deal about it, you may never know. So it's hard to count and know how many C++ users there are. A lot of the tools are open source. Nobody knows how many people are using Clang. There's no user license for Clang. Who knows how many people are using it? This is, and again, I want to point out, this is several years old now. We believe it's probably closer to 5 million today, but at the time of this survey, we were about 4.5 million C++ developers in the world. That's more C++ developers than there are Python developers. Not by a whole lot, but it is. One of the things that really surprised me, because I have a very North America bias, almost all the C++ programmers I knew back then, I've met a lot of people from Europe now, but back then everybody I knew was in North America. And all the famous people were in North America. You know, Scott Myers and Herb Sutter, everybody was in North America, right? So that must mean that's where they all are. Wow, I was shocked. There are more people in Europe, more people in Asia Pacific, 50% more in each of those than there are in Europe. And even in South America. Who ever heard of a programmer from South America? Almost half as many people as there are in North America, right? That was a real eye-opener for me. This is looking at how C++ compares to other languages. And when I first looked at this, it was kind of a little surprising to me, but what I'll tell you now is when we recruit student volunteers for C++ now, we get resumes from students all over the world because we will pay their expenses. We're very, very selective. We don't take very many students, but the ones we do take get to come to Aspen and be part of C++ Now, which is a great conference. It's an incredible opportunity. So we get great resumes. And what we're finding out is that we're consistently getting really impressive resumes from Eastern Europe, Russia, Belarus, these areas. There's some serious C++ being taught somewhere there. You get one or two good students, you just assume, well, you know, that's just a distribution of good students. But when you're consistently getting good resumes from there, that means somebody cares about that there. Somebody's doing important work there. This is the industry distribution. It looks like finance is really represented. I don't know if that's really because the finance people pay a lot for the job ads. I don't know what it is, but it gives you a little bit of idea about where C++ programmers are working. So this is a podcast. How many of you are familiar with CPP Cast? Okay, that's not nearly enough. There's no commute time here? I mean, there's nothing better than when you listen to the podcast, they walk you through the code. They do. They describe it. They say, okay, and then there's a semicolon, and then on the next, no. They're interviews. They never look at code. It doesn't work that way. They do interviews. And it's great. It's a lot of fun. It's fun to listen to. So they've now at episode 195. So get on board quick, and you can see what the big surprise is going to be for episode, I don't know what it is, for 200. But it's over 4 years now that they've been doing this. There's also another one called CPP Chat. That's the one I do. It's both video and audio. It's not nearly as good, frankly, but we have a lot of fun because we're doing it for more fun, and so we're having fun. Anyway, There's an awful lot of places where C++ can be found online. Stack Overflow, when I pull this up, which is several years ago when I first was doing the book, was over 500,000 questions. There's a community called cprogramming.com, which is, again, a resource for people answering and asking questions about C++. We've talked about CPP Reference. CPP Reference is actually a wiki. It's an amazing opportunity. And look, C++ 20. And that's actually a pretty old picture that I pulled off of there. They keep that updated. If you think about it, we're talking about how quickly the compilers and the library people keep their features up. These people are just documenting it. They can get it up a lot faster. As soon as it's in the standard working draft, they're starting to document it. And what's nice about it is if you go to this website, every piece of information on there is tagged to say when what version did it become and what version did it go away. So some things do get deprecated and some things do get changed. And anything that's been in C++ the whole time won't have any tag at all. But everything is tagged so that you can look at this and say, well, I'm looking at, I'm targeting C++ 14, what's available in C++ 14. Absolutely amazing resource. And then Reddit. Wow, Reddit. So the Reddit was actually created, I don't know if you can see all these dates, in 2008. 2008 it was created. But 2008 was still in the bad time, in the dark time, in the Java time, right? So it didn't really hit 10,000 users until 2012. It took 4 years to get to 10,000 users. But notice, from 2012, it got another 10,000. It doubled from October to April, about a year and a half. About a year and a half, it doubled in size after taking 4 years to get there. But then notice what happens. It gets to 30,000 the next year, and then 40,000 the next year, and then 50,000 the next year going from September to June. It's getting earlier in the year. And then in February of 2018, it made it to 60,000 people. It is an incredible community that's looking at C++ on Reddit. It's an amazing thing. It's now at 85,000 users. I just checked it last night and updated this. Actually 84,000. Okay. All right. And then Stack Overflow, I checked it last night. It's at 600,000 questions that are tagged C++ questions. This is actually a community that has come up. It is the Slack community. It is an open community in the sense that Slack is designed to only be invite only. However, I will tell you how you can get your invite, because you're a personal friend of mine. I can get you in, right? Okay, here's the deal. There's 150 channels. So there's channels for events. There's a C++ Now channel. There's a CPP channel for C++ in Paris. Every event has its own channel. There are topic channels. There are channels that are like just basically for books, for Boost. There's all sorts of channels. There are 12,000 members, and that's over 1,000 active members every week. It's a very, very popular thing. Here's how you get your invite. You go to cpplang.noun.sh. That is the auto invite. You put in your name and your domain, and you say you're not a robot. You click this, and you will get an invite. If you want this and you didn't write it down, contact Mike, and I'll see to it that he gets the URL. Okay? So you can join that. This is what it looks like, and it looks very, very similar to the pound include. Yeah. The website that Mike invited you to go to, the pound include website, right? Or Discord, yes. So it looks very similar to that. But here is UG Toronto. I guess I didn't mention this. There's also every local user group. I shouldn't say every local user group, but there's a lot of local user groups that have a channel on there. And I tend to be a member of everyone I can find. All right. There's also on this SuperFAQ, there's a list of user groups worldwide, which has a map that at this point is pretty outdated, but it's listed. There's also a calendar of community events where we put any of the conferences on there. And speaking of conferences, all of these conferences are since 2010. All of these conferences. And before 2010, there are no C++ conferences that are in existence before. I mean, there were some and then went away. None in existence now. Going native actually has retired. It happened twice. C++ Now used to be called BoostCon, and it does predate that, but the name was changed to C++ Now. It's the one that's in 2 weeks. This is in September. Meeting C++ has been in Europe And it started actually the same year at C++ Now did, and has been bigger every year, because even the first year it was bigger than C++ Now. There's an audio developer conference that happens in London. There's a C++ Russia conference. There's one in Belarus. There's one in Italy. There's one in, I think that was the one in Spain. There's one in China. There's a C++ for embedded in Northern Europe. There's an Asia one that's in either Australia or New Zealand. He's going back and forth. All of these things, and there's 2 new ones in 2019, which Mike told you about earlier. One of them is C++ on C, and the other one is Core C++ in Israel. The C++ on C was in England. It's already happened. The one in Israel is coming right up. There is also on the SuperFAQ, there is a list of all of the conferences worldwide, and it gives the dates, lets you know what registration's open and when the call for submissions are open. That's just recently. I used to just have a list of conferences with links. But there's a couple of guys who maintain this for their own local company to try to get people to go to conferences. And they said, hey, would you mind if we did? I said, would I mind? So yes. So they're maintaining it. It's a great list. It's got links to everything you want to know about a conference. Absolutely wonderful. The last thing I want to tell you about is this guy here. This is Robin Kuzman. Robin was one of our volunteers at C++ Now. And he came to me. Now, Robin lives in Seattle, lives in the United States, but he's from Russia, even with a name like Robin. He said he's never met a Russian named Robin. He doesn't know how he got named Robin, but that's his name. And he said to me, he said, John, would you mind if I took the C++ Now videos and put them on my website with Russian translation on them? And I said, well, I wouldn't mind, but how about if we just put Russian translation on the ones that are on YouTube? Let's just let everybody have the Russian translation. And what we actually ended up doing was we started looking into it, and we realized the first step to making the translation is just captioning them. So what Robin has done is he started something called the Video Access Project. And the idea is that we are captioning videos, C++ videos, so that if maybe you have a hearing issue, so you would rather read it than hear it. Maybe you have a language issue, so you can read English better than you can hear spoken English. And also, this is the first step, then, to making translations. So if you want videos in Russian or whatever language you'd like to see videos in, then start working with Robin. Go to his Video Access Project at cppvapwiki.com, and you can see where they've made some progress. And you can see which videos have already been captioned. CPPCon is actually paying a professional organization to caption the videos. Now, YouTube automatically captions videos, but if you've ever seen the quality of that, and then you think about how is that going to do for a technical talk where people use variable names and things like constructor and destructor, it turns out that although I think YouTube captioning is wonderful, it just isn't appropriate for us. We paid a company to do that captioning. It's professionally captioned, but we aren't paying anybody to do translation. So if you would like to do translation and you speak another language, it's Robin will tell you, you download the file, you translate the file, the time codes are already there, and boom. And it's anybody in, it's YouTube. Anybody who goes to YouTube can just say, I want the Russian translation, or I want whatever translation you guys are willing to do. So you've been great. That's what I wanted to talk about tonight. I'm sure we ran long. I didn't even want to check what time it was because I was afraid it was long. But you guys have been very patient, and I appreciate it very much. I'm more than happy to take questions. You can tell that once I start talking about C++, you can't shut me up. So does anybody have anything they want to question about? I think he's got a microphone headed your way by airmail.
I know you can throw it, but I think you should.
Hello.
Hello.
Okay. So I heard that in the 70s and the 80s, memory was faster than processor speeds, like 100 nanoseconds versus like a microsecond for a clock cycle on the CPU. And so all the programming languages then basically assumed, variable access was instant. And then there was a crossover point, and then there was cache memory, which kind of tried to hide this. But not a single programming language today, makes reference to the fact that there are memory hierarchies, and that's what really dictates performance now. GPUs, OpenCL kind of does that, but none of the desk CPU languages do that. Could you comment on that a bit? Is that correct, first of all? And are we stuck in a time warp?
I actually feel very fortunate because in my career, one of the things I did is I worked at A9 at the same time that Alex Stepanov did. I would like to say that I worked with Alex Stepanov, but the truth is he was in research and I was doing I was working on the search engine. But Alex actually did a series of classes. I got to know him well, and I really appreciated him. He's brilliant. But one of the things he told me one day, just out of the blue kind of, he said, well, the STL is outdated. I said, what do you mean it's outdated? Well, we're still developing STL stuff now. What do you mean it's outdated? He said, well, it was written for a different hardware architecture. I said, what are you talking about? He says, well, consider malloc. He said, malloc is much more expensive than it used to be. And I said, you mean because we have bigger blocks of memory? He said, no. He said, it used to be, when we originally developed the STL, everything was single-threaded. We never did anything multi-threaded. Everything was single-threaded. So if you called malloc, it didn't have to take a lock. Now, what is malloc going to have to do? Malloc's going to have to take a lock. So yes, it does allocate much more memory, but that's not significant. That scales easily. The problem is that taking a lock is fundamentally more expensive. He says the other assumption we made is what you were talking about, which is he said we assumed every memory access was equivalent. You can access this memory, it doesn't matter. That was the working assumption. He says it's no longer true. What's true now? Caching. It's all about the caching. And as I pointed out at CPPCon in 2014, all the sessions we're talking about, well, it's a bit of an exaggeration, but yes, we're talking about caching. What this means from the point of view of the STL is probably that it was things that use malloc for each item, which are things like list, set, the red-black tree implementation, set and map, the hash maps, all of these things require an allocation per object. That's probably more expensive than what was intended in a relative sense. The other thing is those things which are not contiguous, because again, contiguous memory is your friend when you're doing caching. So what is that? It's the same things, those same things. Relatively more expensive. So vector, array, these are the things that we like to use. I'm not really sure what the language can do, but I'm sure there's people who are thinking about how you do this. I don't know what the answer to this is. It is absolutely true that memory hierarchies are changing the way we're thinking about programming, but it's not obvious what we do and how we do that. What I'm certain of is that the people working on C++ understand this problem and are trying to figure out how to exploit that performance. And I don't have a better answer for you, and I wish I did. Come on, somebody ask me an easy question.
Similar to the last question, what about the fetch and prefetch intrinsics? How does that address the three-level cache?
I can't really address that at all. I don't know. I can't say anything intelligent to that. I'm sorry. No other questions? Did I exhaust you? Yeah.
When's GCC, G++ going to support the parallel extensions?
Oh, I certainly can't respond to that. I have no idea. Yeah, I don't know. You know, one of the interesting things about GCC is really, really important to the C++ community, as you can imagine, right? One of the big three compilers. Clang's very important. Microsoft's very important. I'm not going to try to rank them, but clearly those three are really important to the C++ community. If you go to C++ conferences, which I do, you will see lots of people who are from Microsoft there. You'll see lots of people working on LLVM and Clang there. You will not see lots of people in GCC. Why? Because GCC itself is for the most part written in C. So they do have some C++ going into the compiler, but the compiler is actually mostly written by C programmers. And so they're not really as much part of our community. And I try to get them, you know, Jonathan Wakely, who's in the library people, they're, of course, C++ programmers. They're not writing the C++ standard library in C. They're C++ programmers. So people like Jonathan Wakely are involved in our community, but we don't get a lot of people from the compiler. And I try. They're more than welcome, and I reach out to them, but we're not getting a lot of participation yet. That's disappointing to me. The people from Clang are all over the place. The people from Microsoft are very visible at the conferences. Yeah?
Talk about the dynamic after you release different versions of the standard.
Uh-huh.
How there was a big period of inactivity.
Yeah.
Where you were like, waiting for feedback, and then it came, and there was some iteration.
Yeah.
Can you describe the dynamic now where, the standard is barely leaving the building and the features are already in the real implementation?
Yeah.
So can you talk about some of the challenges of that? Because obviously it means that, having the big periods of inactivity has some challenges, but perhaps it gives you some flexibility to make modifications. Whereas if, people are waiting on bated breath for the things that you say, and then there's implementations coming out immediately, does that change the way you approach the standard, or how do you correct mistakes? Because mistakes are inevitable.
So I didn't really talk a lot about why we didn't have a release in the 2000s of the standard. There was actually a release in 2003, but it was a really minor, it was a bug fix release, if you will. No new features were added. It was literally the bug fix. In fact, it was essentially when they released the 2003 release that they switched gears and said, okay, let's start working on new features. And what they did at that time was they listed the features. They said, well, we want multi-threading, we want lambdas. They listed what they wanted to have in the language. And they said, when we have these features, we will ship the next standard. And of course, they completely underestimated how long it would take. We have a bunch of software engineers underestimating how long it will take to complete their work. Can any of you imagine that situation? I'm asking you to please stretch your imagination and try to imagine that it was wasn't this a shock. So they actually then decided to change the process at that point. When they finally released 2011, they said at that point, and it was well understood that 13 years was way too long between releases. But they felt trapped because they said, this is what we're going to have in the next standard. And one of the things that happens is when it drags on a long time, what happens is somebody comes up with a new feature. You come up with a great idea, and you say, oh, put this in this, and they say, oh, no, that will delay this. No, but it's such a cool idea. And you push really hard because if they don't take it, and it has to go in for the next standard, and that takes another 13 years, you may be retired before any users use your features. So you push really hard, and then what happens is the committee spends all its time trying to prioritize things instead of actually getting any work done. So in 2011, the committee itself decided we're no longer going to be feature-driven. Now we're going to be date-driven. And so in 14, in 17, in 20, we will have releases. Now, you can never guarantee. It's possible that something will happen, cause 20 to slip, and it'll be 21. But I'm telling you that the plan is we ship every 3 years what is in the working draft. And the working draft, you can think of that as, in fact, it literally is in GitHub, so it's the tip of tree, right? So what happens is papers come in, they get discussed. The normal thing is the paper gets kicked back several times, but finally it comes in, people say, yes, vote that into the working draft. And then every 3 years, we ship the working draft. Now, it's not quite as blind as that. It's not like, oh, look what time it is, we better ship the work. No, we know that's coming. And in fact, we're now in a period where you can make changes to the draft, but you cannot add a new feature. You can change existing features, but you cannot propose a new feature for 20 because we're too close to making that release. So it's all planned. And one of the things that makes this spend less time, there's still arguments about priority. Can we get this in this release, whatever. But people aren't crying to get things in the release because if it's delayed by a release, it's only delayed 3 years, and it's not really delayed 3 years. Because as soon as it gets in the working draft, there's going to be implementations of it within months. Depends on how complicated it is. So users will see your work within a couple of years of it getting approved. Absolutely, right? And so that causes you to not push so hard. Particularly, you see the committee's very busy. It's not like they're wasting their time. It's not like you're saying, come on, guys, talk about this. No, there's important stuff going on. So there are challenges associated with this. Now, this is the first time, at least from my point of view, that we're seeing a phenomenon we haven't seen before. When the standard was released in '98, we introduced at that point namespaces. There were no namespaces before that. And the standard library was put in a namespace. in C++ 11, we had some new language features like initializer lists. And all of the library features can be initialized with, at least the containers can be initialized. You see. So what I'm saying is there's new language features, they get put in the library. With C++ 20, we have voted in contracts and concepts, and there simply is not time to conceptify and contractify the standard library. And so for the first time, we're going to be shipping features in the language that are not yet used in the library. I think this is a first. And it comes out of the fact that with a 3-year ship cycle, and we just got both of those in. They just came in recently. Nobody wanted to wait till the next cycle. They seem to be ready. And nobody wanted to say, well, let's wait until we can do the whole library, because that could be very contentious. That might take more than a cycle to get the library finished. So nobody wants to wait on that. So we have language features that will not be reflected in the library really for the first time. And I think that's a result of this faster cycle. I don't know if that answered your question, but it might have been interesting.
Okay, let's take one more time to thank our speaker.
Oh, thank you very much.
Oh.
I wanted you to have these Canadian chocolates. And what I hope is a carry-on size maple syrup.
Oh, thank you very much.
I can't imagine a better start to this user group than that talk.
Well, you guys, I can't imagine a better start to the user group, not because of the talk, but just because of what you have done. This is an incredible turnout. There's a lot of energy here. I got a chance to talk to people. I hope you guys aren't going to rush right off and we still have a chance to talk. But you've done an amazing job of getting this started, and I'm so proud of this. I'm so proud to be part of this. Thank you very much.
Thanks so much. Okay, just a couple procedural matters. Our next event is already scheduled for May 28th. It's going to be the topic will be simulation in C++, and it'll be by Amazon's Damien Vicino, who is here tonight. If you would like to speak at a future event of this user group, please contact me. We are always looking for good speakers. And if you are worried about making a good presentation, if you're worried about making a good proposal, go to the Include Discord, and people will help you. Also, we're looking for sponsors. Autodesk has been fantastic, but we want to keep this thing going. We want to do it every month, and that means we need continued sponsorship. So if you know somebody who can authorize money to the group, let me know. Okay, so afterwards we're just going to have some dessert and we're going to socialize. But first, I would like to see a show of hands if you are currently looking for an internship, a job, a consulting role, anything like that. You are looking to get hired. Okay, mark the hands. Keep them up. Let's have a look. Okay, now raise your hand if you are hiring in some capacity or know of somebody who is hiring. Okay, have a look at those. Okay, so as you eat your dessert, perhaps you guys should talk.